If humanity wants to survive, we will eventually have to dismantle a planet. This sounds insane, but in physics, it's a real, unavoidable survival problem we'll face sooner or later. Because every year a civilization grows older, its demand for energy rises, and Earth's limited ability to dissipate heat will eventually be pushed beyond its limits by us. So scientists began using ideas like the Kardashev civilizational scale and Dyson swarms to calculate the future road of civilization, from coal and oil to fully harnessing a star. But the key question is this: at which step would a civilization be forced to dismantle a planet? So in the next few minutes, we'll start from the charging cable in your hand and talk all the way to the day a planet must be taken apart. And when Earth is no longer enough, will you or your children still have a place to go? Before we start, we must clarify the universe's true currency. In physics, energy is the only universal currency. From quiet cellular metabolism to the violent radiation of a quasar, they are doing the same thing, capturing energy, then releasing it according to their rules. A system's complexity has nothing to do with appearance. It depends only on how much energy it can control. A civilization is no different. Energy isn't just resources. It's the absolute ceiling that determines how far a society can go. No matter how flashy the technology or dreams, they are only decorations if energy cannot support them. So where are we on that scale? In the 1960s, Soviet astronomer Kardashev proposed a set of civilizational levels to measure a civilization's advancement. Don't look at its spaceships, look at how much energy it can use in a year. And according to that scale, humanity hasn't even reached type I. We are only around 0.7. Most of our energy still comes from burning coal and fossil fuels. Only a tiny fraction is actual sunlight we capture. Put bluntly, we are scavengers living on the surface of a planet. But as long as civilization lives, it cannot remain still. Populations grow, cities get brighter, servers spin faster, rockets lift off, and humanity's total energy consumption only goes up. Even if it rises by only 2-3 each year, an exponential curve eventually becomes a cliff. Civilization is a heat engine. Everything computing, transportation, manufacturing consumes energy and releases waste heat. All this heat must eventually be dumped into space through Earth's surface. But Earth's heat dissipation capacity has a physical upper limit. A true Type I civilization would maximize the planet's entire energy budget, controlling the climate, using tectonic energy, capture every photon hitting the surface. Sounds powerful, but here's the catch. As long as machines and cities run, they all turn into wasted heat that must leave the planet. Even if we build perfectly clean fusion reactors with zero emissions, the wasted heat is still unavoidable. It's entropy, the law no one escapes. If one day, humanity's total power output matches the sunlight Earth receives, what happens? Physics has a cold answer. Earth boils, the surface temperature skyrockets, the oceans evaporate. No war, no asteroids needed. Humanity cooks itself to death. This is the planetary saturation point. The walls a Type I civilization crashes into. So moving from a planetary civilization to a stellar civilization looks like an upgrade, but it's really a survival problem. Cross it, or be erased by thermodynamics. From a physics view, the solution is clear. Separate where we live from where we generate energy. Stop treating Earth as a giant battery. Start treating the sun as the real engine. How big is the difference? The sun releases more energy every second than all civilizations combined have used in human history. And even a full Type I civilization captures only a tiny fraction. The sunlight that hits Earth, just a 100,000th of the sun's output. The remaining 99.99999% is wasted into deep space. At this point, civilization must shift perspective from mining planets to extracting energy directly from the stars. Which brings us inevitably to the Dyson sphere. People imagine a giant shell surrounding the sun, the ultimate structure. But real physics ruins this dream quickly. No material can withstand the gravitational stresses. A rigid shell is unstable and would collapse into the sun. The realistic solution is not a solid shell, but a swarm, a Dyson swarm, millions or billions of independent structures orbiting the sun, solar collectors, mirrors, O'Neill cylinders. Together, they capture as much stellar energy as possible. The challenge is no longer magical materials, but mass production and logistics. On a solar system scale, where do we get enough material? Even dismantling Earth would only build a thin layer, and we obviously can't disassemble our home, so civilization must find another planet to mine. And the best target turns out to be Mercury, close to the sun, 7 times the energy per square meter, made mostly of metal-rich rock, ideal for manufacturing. So as a civilization approaches Type 2, Mercury quietly becomes the solar system's main construction quarry. But humans with shovels won't dismantle a planet. A Type I civilization will use self-replicating machines. This is the von Neumann probe idea. Build one automated factory on Mercury. It mines ore, uses sunlight to power itself, and builds another factory. Each new factory builds more factories. 1 becomes 2, 2 becomes 4, 4 becomes 16. In a few years, you have millions. Mercury becomes covered in automated industries, its crust peeled away layer by layer, materials sent upward. To assemble Dyson Swarm components, launching them requires not chemical rockets, but electromagnetic mass drivers, lined across Mercury's surface. These launch units, using the sun's energy, the same energy the Dyson Swarm is starting to collect. Over decades or centuries, the inner solar system changes. Streams of metal modules spiral outward, forming a thickening cloud around the sun. Seen from the outer planets, the sun grows dimmer, partially obscured by a cloud of machines. At this stage, civilization enters its stellar era. But a Dyson swarm is not just a power plant. Using the same materials, we can build O'Neill cylinder habitats, giant rotating space worlds, with artificial gravity and ecosystems. Dismantling Mercury could create thousands of Earth-equivalent worlds. This is where humanity transforms. No longer forced to adapt to planets. No longer praying for a world with water and air. We design our own environments. A star becomes a tree, with thousands of artificial worlds orbiting it. Habitable zone is redefined. Not where liquid water naturally exists, but where energy and infrastructure reach. With a Dyson swarm, the energy scarcity ends. Material scarcity ends. The concept of economy, born from limited resources, begins to fade. Matter becomes programmable energy. Gold can be synthesized, water reformulated, complex organics assembled on demand. Poverty becomes a physical impossibility. The question shifts from, how do we survive, to, what do we want to become? These habitats became experiments in civilization. Some replicate the old Earth, forests, farms, seasons, fully automated beneath the surface. Some are zero-gravity forests. Some shift life into digital existence. Minds living inside megacomputers, cooled in the shadow of the Dyson swarm. Humanity becomes the designer of itself. But such power brings danger. The same laser arrays that pushes starships can sterilize a planet light years away. The same energy that builds worlds can destroy them. Maybe the great filter is not behind us, but ahead. Not that civilizations cannot build Dyson swarms, but that they cannot handle the responsibility of controlling a star. Yet from the inside, a Dyson swarm is still hopeful. It represents mind triumphing over matter. From inside an O'Neill cylinder, you look towards the sun, not as a blazing, indifferent gods, but as a tamed engine, powering countless worlds. At that moment, you realize humanity is no longer a passenger on Earth. We are the pilots of the solar system. The universe ceases to be frightening. It becomes raw material, waiting to be shaped. Kardashev's scale stops being about energy consumption. It becomes a measure of how much light a civilization prevents from being wasted in the void, how much starlight it turns into life, consciousness, and beauty. From a fire in a cave to a machine cloud wrapping a star, the arc is long, but the logic is continuous. It is a survival plan, written with gravity and light. Today, when we watch rockets punching through the blue atmosphere, we may only be seeing a species learning to walk. The energy has been waiting all along, and those stars, they were never just lights in the sky. They are destinations.